Hey there, my name's Vincent, creator of InfoHazard Games, and I'm making an FPS called Astral Horizon. This is the first video in a series where I'll discuss some of the more interesting technical challenges I face working on the game. I'll be using Unity, so you may need some knowledge of Unity and C# in order to follow everything, but the concepts and techniques should apply to any 3D game engine like Godot or Unreal. For this first video, I'm going to introduce how I handle character navigation. So, one of the game's core features is flying with a jetpack in all 3 dimensions. You're in space after all, so there's no global up direction. Now, if you've programmed 3D character movement before, this probably sounds pretty simple to do for the player character. The issue is that NPCs can do this too, and they're gonna need some way to navigate around the level and not bump their heads into every other wall. Before we get to solving this, I'll go over some pathfinding concepts. A pathfinding algorithm usually finds the shortest path between 2 points that might have some kind of walls or obstacles in the way. There are many pathfinding algorithms, but one of the most popular in video games is called A*. I'm not going to get into how A* works here, but there are plenty of great videos on the subject already. What most of these algorithms have in common is that they use a type of data structure called a graph. A graph is just a collection of nodes and the connections between them. For example, a driving directions app might use a graph where the nodes are intersections and the connections are roads. Now, roads naturally form a graph structure, but in a game level we usually don't work with nodes and connections like that. As far as Unity is concerned, a scene is just a big mishmash of renderers, physics shapes, and scripts. However, we can usually create a graph for navigation using a common engine feature called a NavMesh. A NavMesh is created by turning all walkable surfaces into a super simplified set of triangles. The triangles form the nodes in a graph, and their shared edges form the connections. NavMeshes work great when characters are always walking on a floor, and they can even handle short non-walking bits like parkour through off-mesh links. What they're not good at is when characters can fly in whatever direction they want. In a situation like this, there's no way for the NavMesh to find a path between these 2 points, since it doesn't consider this mid-air obstacle. Initially, I did try solving this by placing a bunch of off-mesh links, but it simply didn't give me the flexibility I needed to have the characters believably and intelligently fly around the level. Enter my first solution to 3D navigation, the nav grid. My idea here was to divide up a region into a simple grid of voxels. An editor script would loop through each voxel and use a physics query to determine whether that cube is open or blocked. A blocked cube is considered impassable to the player, while an open cube is a valid pathfinding node with connections to any open adjacent nodes. That structure formed a graph, which could easily be used with A*. But I ran into a pretty big problem. When setting the voxel size, I could either set a small size and get lots of precision, or set a large size and save memory and pathfinding performance. In a 3D grid like this, as the precision increases linearly, memory and performance cost increase cubically. A grid that's just 50 voxels on each axis has 125,000 total voxels, definitely more than we want to deal with for every pathfinding call. It was time to go back to the drawing board. Next, I decided to try out an Octree-based approach. An octree is a cube that can be subdivided into 8 smaller cubes, which can in turn be divided themselves. In the new system, we start again with a uniform grid, but with a very large cell size. If a cell is completely open, then we don't need any more precision within that cell. However, if a cell is partially blocked, we subdivide it, and do the test again for each child. If the child is open, we're done, and otherwise we divide it again. We also need to have a max depth, to prevent this from recursing into infinity. Then, at the end, if we discover that all of a cell's children are blocked, we can mark the cell as blocked and remove the children. Once the octree is built, we still need to determine the connections between cells before we have our graph. In a simple grid, this was super straightforward, but it gets a bit messy when each cell has neighbors of different sizes. After a lot of experimentation and many bad MS Paint diagrams, we now have a graph that we can use in the A* algorithm. Plugging the system into the NPCs, it seems to work pretty well. They can navigate freely in 3D space, and there's a decent balance between performance and accuracy. I built this Octree-based system way back in 2019, and I've been using it since then. But there are still some major issues, and lately I just wasn't feeling happy with it. I'd like it to have better accuracy, especially in tight spaces, but the performance still suffers at times as well. I'd also like it to connect with a NavMesh for characters that can both fly and walk on surfaces. That would enable a single path to include walking and flying parts. So in 2022, I went ahead and rebuilt the whole system from the ground up. In the next video, I'll describe how this new and improved navigation system works. Thank you so much for watching, and stay tuned to learn more.